Solutions, Part 1, Energetics of the Solution Process. Imagine a positively charged particle is stuck to a negatively charged one. In order to separate these, energy must be absorbed. So you need to pull these particles apart and apply energy to the system. This is called an endothermic process because energy is being absorbed. Now, conversely, imagine a positively charged particle bumping into a negatively charged one and setting up attractive forces. Here, energy is released. This is called an exothermic process. Now let's apply this to bonding, chemical bonding. Whenever bonds are broken, energy must be absorbed, and that has a positive value for enthalpy. We'll show you why in just a minute. And if two atoms form a chemical bond, then energy must be released as attractive forces are set up, holding the atoms together. This is an exothermic change, and the enthalpy will have a negative value. Now let's consider the energies involved in the solution process. First, you have a solute. Might be sodium chloride, it might be sugar, but you need to break the atoms or molecules apart from the crystal lattice that they're locked in and separate them so that the solvent, let's say water, can surround those particles. So the first step is to break the solute-solute attractions. This value is the crystalline lattice energy reversed. Crystal lattice energy is the energy released when the particles come together to form the crystal, but you need to break the crystal apart in the process, and therefore it's going to be an endothermic change with a positive delta H. And we'll explain why it's positive in just a minute. So first step, solute-solute attractions need to break. Second step. The second step is for some of the solvent-solvent attractions to break. For example, if you're using water, you've got hydrogen bonding going on, and some of those hydrogen bonds need to break so the water molecule can go off and surround the solute. This too is an endothermic process because we're breaking attractions between particles. But finally, the energy payoff comes when we mix together the separated solute with the separated solvent particles. New solute-solvent attractions form, and of course this is going to be an exothermic process. Another factor that determines whether a process will be spontaneous or not is the concept of entropy, which is a measure of the energy dispersal throughout a system. You can think about it as the degree of randomness of a particular system. Processes that lead to energy being spread out over as large a volume as possible tend to push that process to be spontaneous. And you can really see that if you have two gases, neon and argon, separated by a barrier in a container. Well, the minute you remove the barrier, the neon and argon mix. It's just common sense. Well, that's an example of entropy increasing. The same idea would exist if you had a container of pure water separated by a barrier and a container of water with salt dissolved in it. Remove the barrier, and the salt spreads out throughout the whole system. These are both examples of entropy increasing. We'll learn more about entropy in the chapter on thermodynamics. Another concept's been developed to simplify the calculation of the heat of solution, and that is if we take the solvent-to-solvent enthalpy, the enthalpy required to pull the solvent particles apart, and move that over to combine that value with the enthalpy of mixing, the energy given off when the solute and solvent attract each other. So these two concepts combined give us the enthalpy of hydration, And now we only have two enthalpies to consider when we calculate the enthalpy of the solution. Enthalpy of solution is equal to the enthalpy of hydration minus the crystal lattice energy. So here's a question for you to consider. You can try it out. I would advise you pausing the playback, trying to do the calculation, and then comparing your answer with mine. Here's the answer, minus 797 kilojoules per mole. When we put a solute, such as sodium chloride, into a solvent, such as water, water molecules are drawn to the positive sodium ions and to the negative chloride ions. Attractive forces are established and hydrated ions are pulled off of the crystal lattice. At this point, the solution is said to be unsaturated, but as the population of ions in solution grows, some of the ions collide with the remaining crystal lattice and stick onto it. Eventually, the rate at which ions collide with and are incorporated by the crystal lattice equals the rate at which ions are coming off. At this point, equilibrium has been established and the solution is said to be saturated. This is a dynamic equilibrium. In some cases, it's possible to have more of the solute dissolve beyond its solubility at that temperature. This is an unstable solution which is said to be supersaturated, and crystallization can occur if a seed crystal is introduced. So you have unsaturated before equilibrium, at equilibrium, it's a saturated solution, and the unstable supersaturated solution. Except for gases in which the particles are independent, solute and solvent particles must be attracted to each other. So there's ionic attractions. For example, when a positive ion is attracted to a negative ion, sodium chloride. These are the strongest attractions between particles with a very high boiling point and melting point, and they tend to be soluble in, of course, polar solvents. Look at that bond energy, 400 to 4,000 kilojoules per mole. Next, dipole-dipole attractions, where the positive end of one molecule, which is a dipole, is attracted to the negative end of another dipole molecule. This is a medium range of attractions between particles with a much lower boiling point and melting point than ionic attractions. And these two tend to be soluble in polar solvents. Finally, you have the weakest type of interparticle attractions, dispersion forces. All molecules have these, but they're not important when you have dipole-dipole and ionic attractions because those are much stronger. These are the weakest attractions, and substances held together by dispersion forces have a low boiling point and melting point, and they tend to be soluble in non-polar solvents. Now, what you might want to do is review section 11.3, which presumably you had in Chemistry 1A, the chapter on intermolecular forces, because these not only account for the properties of the liquid and solid states of matter, but also help to explain the solution properties. It's important for you to recall that electronegativity, or more precisely, the difference in electronegativity values between bonding atoms, affects what is called the polarity of the bond. Atoms have different electronegativity values, and the difference of electronegativity between bonding atoms accounts for the type of bond that you're going to have, pure covalent, polar covalent, or mostly ionic, depending on the electronegativity difference. Now, electronegativity plays a role. Here we have acetone, and the electronegativity difference between carbon and oxygen is 1, 2.5 and 3.5. Is definitely a polar. It's not enough just to have polar bonds, asymmetric or lopsided. Compound has both polar bonds. Polar bonds are arranged in a lopsided fashion in the molecule. The substance. So is acetone a dipole? And here you can see another acetone molecule. But acetone is also compatible in water because it is also a dipole. And the Z participate in the attractions. Of course, it's the dipole nature of water that allows it to dissolve so many ionic salts. Here's sodium chloride in water, and the chloride ion is negative, the sodium ion is positive, and each of those ions is able to be surrounded by water molecules and pulled off of the crystal lattice in that fashion. Another concept you covered in Chem 1A was hydrogen bonding, which has a major effect in the solubility of substances. Hydrogen bonding is an especially strong dipole-dipole attractions, and it's caused when hydrogen bonds to the most electronegative atoms, oxygen, nitrogen, or fluorine. This strong bond polarity and the fact that the hydrogen is de-shielded, meaning it can snuggle up close to a negative charge on another atom, allows it to form strong interparticle attractions. And this is of major import in the solution process. So we have some questions on the next few slides. What you should do is read the question and put your playback on pause, and then come back and we'll discuss the answers. So which of these compounds have hydrogen bonding? Well, number 3 does, because there's a hydrogen-nitrogen bond here, actually 2 of them, and here's an OH bond. So 3 and 4 would engage in hydrogen bonding. Which compounds, when pure, have hydrogen bonding? Well, 3 does, there's an OH bond. 4 does, there's an NH bond, 2 of them actually. And that's about it, 3 and 4. Finally, there's the weakest type of interparticle attractions, dispersion forces. These are temporary, instantaneous dipoles caused by electron cloud shifting. All molecules and atoms have them, but they're insignificant if the molecule has ions or if it has dipoles. Generally, the bigger the particle, the bigger the electron cloud and the stronger the dispersion forces are. Attractive forces and solubility. Now, solubility depends on the attractive forces of solute and solvent molecules. There's a saying, like dissolves like. So polar substances dissolve in polar solvents. Groups with an OH, a C double bond O, NH2, etc. are quite soluble in polar solvents such as water because they're able to engage in hydrogen bonding. Nonpolar molecules dissolve in nonpolar solvents. Molecules made up primarily of CH bonds or C carbon-to-carbon bonds are not going to be soluble in polar solvents, but they will dissolve in nonpolar solvents. Many molecules have both hydrophilic and hydrophobic parts. Solubility then becomes a competition between the parts. So which pair in 1 and 2 has a higher water solubility, and which pair in 3 and 4 has the higher water solubility? Number 2 has a higher solubility than 1 because it can engage in hydrogen bonding because you have NH bonds. Likewise, between 3 and 4, 4 has an oxygen-hydrogen bond that can engage in hydrogen bonding. So an example of polar solvents, of course, water is a polar solvent. Ethanol is a polar solvent, has that nice OH on it that can engage in hydrogen bonding. Nonpolar solvents, examples hexane, carbon tetrachloride, toluene. None of these compounds have polar bonds that are arranged asymmetrically around the central atom. So like dissolves like, fully or partially charged particles, ions and dipoles, tend to be soluble in each other because their particles attract each other. And nonpolar molecules like naphthalene dissolve in nonpolar solvents like hexane through dispersion forces. But if you put some pentane into water, they will not mix. The water molecules will not separate because they do not get enough energy in interacting with pentane molecules. So the water molecules stay in their own layer, and the pentane molecules stay in their own layer. An ion or a dipole can induce a temporary dipole in a non-dipole. We all know oxygen is soluble a little tiny bit in water, but it makes all the difference because that's how aquatic life gets their oxygen, through dissolved oxygen. So how does oxygen, which is about as nonpolar a molecule as you can get, come to have at least a little solubility in water? Well, the answer is that the water, being a permanent dipole, as it approaches the oxygen, can induce a dipole. The negative end of the water molecule can repel the electron cloud around the oxygen, pushing the electrons to one side, and the side closest to hydrogen then has a positive charge. So there's a weak interaction here by this induced temporary dipole. Okay, see if you can decide which of each pair is going to be more water soluble. Turn off your playback and then come back, and then I'll discuss the answers. Okay, between propyl iodide and propanol, it's the propanol with an OH bond that can engage in hydrogen bonding that's going to be more water soluble. Here's a 4-carbon chain with an OH and a 3-carbon chain with an OH. The 3-carbon chain is going to be more water soluble because carbon chains are not polar. So the more carbon you have in a carbon chain, the less soluble the compound is going to be, the less polar it's going to be, the less important the OH bonding is going to be. So the 3-carbon chain has it. In which solvent will sodium chloride be more soluble? Again, the one with fewer carbons is going to be the more polar molecule. In which solvent will ethylene glycol be more soluble? This is antifreeze, by the way. And with 2 OHs on 2 carbons, it's going to, of course, be more soluble in water, certainly more so than hexane. And finally, diethyl ether is going to be more soluble in ethanol because ethanol is less polar than water is. Here's a question for you to read. Pause your playback and I'll come back and discuss the answer. Of course, the answer here is going to be dispersion forces because both of these compounds do not have hydrogen bonding and are not dipoles. How about between acetone and chloroform? Acetone, because of its shape, is going to be a permanent dipole, so is chloroform. So I would expect dipole-dipole attractions. Ammonia and water, well, that's easy, hydrogen bonding. And sodium ion and water molecules, that would be ion-dipole attractions. Now let's talk about the solubility of gases in solutions. You all know when you pop the top of a can of soda pop, the gas inside, carbon dioxide, rushes out. That's because you've released the pressure and the carbon dioxide is not as soluble in the liquid at a lower pressure. So pressure is one factor that determines the solubility of a gas in a liquid. The other is temperature. Which fizzes more when you pop open the top? A can of cold soda pop or warm soda pop? You've all had the experience of opening a can at room temperature and having it spray all over the place. That's because all gases are more soluble in cold liquids than warm liquids. So here's a question. Which conditions most increase the solubility of a gas in a liquid? And of course, that's going to be high pressure and low temperature. That's me making seltzer. I've routinely done this for 25 years, make my own seltzer. But the solubility of a gas is directly proportional to its partial pressure, or the pressure of the gas over the liquid. And there's an equation called Henry's law that describes this relationship of solubility to pressure. The solubility of a gas is equal to the Henry's law constant, Kh, times the partial pressure of the gas. And you can see the Kh values for 5 different gases here. Now, just imagine if the partial pressure is 1, say 1 atmosphere, then solubility is directly proportional to the Henry's law constant. The higher the Henry's law constant, the more soluble. So which gas here is going to be more soluble at a given pressure? Oxygen, nitrogen, carbon dioxide, ammonia, or helium? And here you peruse, and you see the one with the highest Henry's law constant is ammonia, and that's the one that's going to be most soluble at a given pressure. So here's a Henry's law problem. What pressure of carbon dioxide is required to keep the carbon dioxide molarity at 0.12 molar at 25 degrees? And what you need is the Henry's law equation, and you need the Henry's law constant for carbon dioxide. Figure it out, and the answer is going to pop up next. So when you're ready, come back and check your answer. All right, here it is, worked out, and the answer is going to be 3.5 atmospheres.